Okay, so we have seen that our variables are co-integrated, so we can run the VECM model. So I go to quick, then I go to estimate var, then here I select VECM model, right, and I put my variables. Cons is the dependent variable and EX and GDP are the independent variable, and actually this one is our target model, where cons is the dependent variable and EX and GDP are the independent variables. And here the lag, we take lag 3 because we have been advised by the lag selection criteria to take lag 3. So I have taken lag 3, and also I go to co-integration here, and here the number of co-integrating model, so actually it should be 1, that we have received from the Johansen test of co-integration, that there should be at most 1 co-integrating model. So here I put 1, right? Okay, then I think we are ready to run it. We are ready to run it. I press OK. Okay, so this is my vector error correction model. You can see from here, right? Vector error correction model, that you can see from here. VECM model, and we have the 1 co-integration model, and that is this one. You can see 1, right? 1 co-integration model, and that is this one, and this is my model error correction. And here what is happening, actually vector error correction model automatically convert the variable into first difference automatically. You can see last time we put cons and cons become decons. Last time we put EX, EX become DEX automatically. And last time we put GDP, GDP has become DGDP automatically. And this one is actually error correction term. And here you can see every variable have 3 lags. Cons lag 1, cons lag 2, cons lag 3, EX lag 1, EX lag 2, EX lag 3, GDP lag 1, GDP lag 2, and GDP lag 3, and constant. And here you can see this is the dependent variable dcons, and these are all independent variables. And here you can see one more things from here. Standard error is the second bracket and t statistics is the third bracket. You can see from here. So this one, actually, suppose this one is the standard error and this one is the t statistics, right? Okay, here so what about this one, minus 28.47? This one is the coefficient of dcons lag 1 variable. And what about this one, standard error? Coefficient divided by standard error, you can get the t value all the time. That is the formula. Again, this one divided by this one, you can get t value. Again, suppose here the coefficient divided by standard error, you can get the t value. But here is no p value or probability value to check whether we should reject the null hypothesis or accept the null hypothesis. So we want to see the p value. Okay, And here our decons, actually this one is our main model or our target model. So we only concentrate here because cons is the dependent variable, right? So this one is our target variable. But now first we try to get the p-value. How to get the p-value, probability value? So how to get, I go to proc, right? I come here, I go to make system, order by variable, I come here. You can see our models. This is my models, you can see. This is model 1. Tcons is the dependent variable. Then DEX is the dependent and DGDP is the dependent. And starting from C1, this is the coefficient, then C2 until C11, and start from C12 again until C22. Again start from C23 until C33. So there are 33 coefficient will be estimated indeed. And this one is called system equation model, right? And what is C1? C1 actually is the coefficient of cointegrating model. Actually this portion is cointegrating model, and C1 is the coefficient of this cointegrating model from here to here. Okay, and here decons actually our main variable, our target variable. So I select it and copy it, select and copy, then I go to quick and estimate equation and I paste it here, the whole model, right? And here the decons is the dependent variable. So I run this model. Okay, you can see decons is the dependent variable, and this is our model so far, right? Okay, and these are the coefficients C1, C2. So here is the coefficient, standard error, and t statistics. This divided by this, you can get t statistics. Okay, this time the p-value has come up, right? But last time there was no p-value, but now the probability value or p-value has come up. Okay, what is C1? This C1 is here. C1 actually is the coefficient of cointegrating model from here to here, right? C1 is the coefficient of the cointegrating model. Okay, what is C1? Okay, so I better delete all. Okay, okay, here actually I delete all these things. Okay, here is the, I talked about C1. C1 actually means we can call it is the error correction term, or we can call it also speed of adjustment towards equilibrium. Okay, equilibrium. Okay, but if this C1 is negative and significant, okay, okay, now actually there are two issues we have to discuss. So two issues. Number one issue is long run causality, that is issue number one. Number two, short run causality, right? There are two issues are here. Okay, so first I talk about long run causality. That I talk first. Long run causality. What is it? Okay, and here long run causality, if the C1, that is this one, if this C1, right, there is C1, if the C1 is negative in sign and significant, then we can say that there is a long run causality running from EX and GDP to cons, right? So that is the guideline. But here our C1, the coefficient is not negative and also not significant, right? Because probability value is 46.18%, meaning that there is no long run causality running from EX and GDP to cons. Okay, that is done. Okay, second issue, short run causality. That is the second issue. Okay, now we want to check whether EX can cause cons or not. Here you can see EX has lag 1, lag 2 and lag 3, and she has 3 coefficients, C5, C6 and C7. So we set the null hypothesis, that is C5 equals C6 and C7 equals 0. All these three things jointly 0 or not. And if they are 0, meaning that there is no short run causality running from export to cons. Okay, so how to check it? I go to wall test to check it. Okay, wall test. How to go wall? I go to view, then coefficient diagnostic, then wall test, right? Then I put my null C5 equal to C6 equal to C7. Are they equal to 0 or not, right? Okay. Okay. So actually if they are 0, in that case C5, C6, C7, 0 means all the EX1, EX2 and EX3 all become 0, right? Okay, so then I press OK. Wall test and null hypothesis and chi-square value and probability. How much probability? 39.46%, which is more than 5%, meaning that we cannot reject null hypothesis, rather we accept null hypothesis, meaning that C5, C6 and C7 is 0. It means that there is no short run causality running from EX to GDP, sorry, EX to our dependent variable, that is cons. Okay. Okay, then we check our second variable, that is whether GDP, right, GDP can cause cons or not. So GDP has three coefficients, C8, C9 and C10, right? So as before we set the hypothesis C8 equal C9 and equal C10, right? We set it equal to 0, right? Whether they are 0 or not, we can check it. Use the Waltz test, right? Use the Waltz test, C8, C9 and C10 Waltz test. I go to view, then I go to coefficient diagnostic, then I go to Waltz test as before, then I write C8 equal C9 equal C10, right? So equal to 0 or not, that is my null hypothesis, right? I select it, okay. Waltz test, right? And null hypothesis is this one, C8, C9, C10, 0, chi-square value probability is 21.61%. It is more than 5%, so we cannot reject null hypothesis, rather we accept null hypothesis, meaning that we accept that C8, C9 and C10 is 0, meaning that there is no short run causality running from GDP to cons, right? There is no short run causality running from GDP to cons. Okay, so what is the summary of this model? Summary of this whole model is there is neither long run or short run causality. Okay, so there is no, I better put it no, there is no long run or short run causality running from EX and GDP to cons. So that is the decision of this model. There is no long run or short run causality running from EX and GDP to cons. Okay, that means there is no association shape, right? So far, short run or long run from the EX and GDP to cons. Okay, now we check how is the model as a whole. That means diagnostic checking, diagnostic checking, right? That we can do. Okay. Okay, so our model is actually this one. This is our model, right? We have seen it so far. This is our model. Okay, in this model, you can see R square value of R square is 62.24%. So it is more than 60%. So I think the model is all right, because normally if the R squared is more than 60%, we can accept the model, and F statistics and the p value, it is significant. You can see it is 0.79%, which is less than 5%, meaning that F statistics is significant, meaning that our data actually fitted well, right? Our model is fitted well because R squared is good and F statistics is significant, so the data is fitted well. fitted good fitted so far. Okay, then we check the residual. I go to view, I go residual diagnostic, then I check the serial correlation, whether our model has serial correlation or not. So here I take lag2, press OK. This is the serial correlation test, observed R square and the p-value. P-value is very small. You can see it is less than 5%, right? Meaning that we can reject the null hypothesis and can accept the alternative hypothesis, meaning that there is a serial correlation in the residual, and that is not desirable, and we are not happy about this model because this model has serial correlation. Okay, then we check some more tests. I go to view, residual diagnostic, then test of heteroscedasticity. I check it. Okay, here I take Bruch-Pregan test, right? Then I press OK. So here is the test of heteroscedasticity. I take observed R squared and the p-value, it is 23.71%, meaning that we cannot reject null hypothesis, rather we accept null hypothesis, meaning that there is no heteroscedasticity in the residual, and that is desirable. This model does not have any heteroscedasticity, right? So that one is good and desirable. And finally we check residual diagnostic. We check the test of normality in the residual. Okay, here you can see the value of the Jarkabera. The probability value is 92.24%. 92.24%, which is more than 5%, meaning that we cannot reject null hypothesis, rather we accept null hypothesis, meaning that residual is normally distributed, and that is the null hypothesis, and we accept the null hypothesis that residual is normally distributed, and that is desirable. So in this model there is only one problem, that is residuals have serial correlation that we cannot accept, because when there is a serial correlation the model is really unacceptable. Okay, so that is the whole thing. Thank you very much for being with me for a while.